IC74LS190 and monitor the output on LEDs.
At the end of this video, you will be able to construct an up-down counter using IC74LS190. Test the counter for counting up and counting down. Let us collect all the tools, equipment and materials required to do this practical. Digital trainer kit with user manual, IC74LS190 with datasheet, male-to-male jumper wire, magnifying lens. Let us discuss the up and down synchronous decade counter. In an up counter, count sequence progresses in ascending order, moving from the lower to higher numbers. Example 0, 1, 2 up to 9. When a clock pulse is applied to the counter, it advances to the next count in a sequential manner. In a down counter, the count sequence progresses in descending order, moving from higher to lower numbers. Example 9, 8, 7 up to 0. Similar to the up counter, a clock pulse triggers the counter to move to the next count, but in this case it decrements the count. Let us discuss about IC74LS190. The 74LS190 is a positive edge-triggered synchronous up-down binary counter IC that contains 16 pins in a dual inline DIL package. The IC74LS190 is a 4-bit counter, meaning it can count in binary from 0000 to 1001, 0 to 9 in decimal. Let us discuss the pin details of IC74LS190. Pin 1 parallel input B, Pin 2 output QB, Pin 3 output QA, Pin 4 active low count enabled input, Pin 5 up down control input, high for down count, low for up count, Pin 6 output QC, Pin 7 output QD, Pin 8 ground, Pin 9 parallel input D, Pin 10 parallel input C, Pin 11 active low parallel load control input, Pin 12 terminal count output, Pin 13 active low ripple clock output, Pin 14 clock input, Pin 15 parallel input A, Pin 16 power supply plus 5 volt VCC. Construction of synchronous up-down decade counter using IC74LS190. Identify the IC with its part number printed on it using a magnifying lens. Identify pin number 1 of the IC and ensure that the IC74LS190 is aligned correctly over the breadboard in the digital trainer kit. Gently insert both lines of pins of ICs on breadboard one after the other. Be careful not to bend the pins or force them into the holes. Ensure that the IC is sitting flat on the breadboard without any pins bent or misaligned. Connect the pin number 8 to ground and pin number 16 to plus 5 volt power supply VCC. Connect pin number 14 to the clock input from the digital trainer kit. Connect pin 15 to D0 input toggle switch. Connect pin 1 to D1, pin 10 to D2, pin 9 to D3. Connect the pin 7 to Q0, pin 6 to Q1, pin 2 to Q2 and pin 3 to Q3. The output LEDs in the digital trainer kit. Connect pin number 5 to the toggle switch S1, pin 11 to toggle switch S2 as shown in the circuit diagram. Switch on the supply and apply plus 5 volt regulated DC supply to the circuit. Setting the decade counter to count up mode and test. Apply logic 0 to the control pin 5, that is S1, and logic 1 to pin 11, that is S2, to make the counter count up through a toggle switch. Apply logic 0 to the pins D0 to D3 using toggle switches. Apply logic 0 to the control pin momentarily and raise it back to logic 1 state with a toggle switch S2. This sets output Q0, Q1, Q2, Q3 to logic 0 levels. Refer to the tabulation of inputs and feed clock pulses at clock input to pin number 14 using single shot pulsar. Record the status of LEDs at outputs Q0, Q1, Q2 and Q3. Set logic 0 to pin 5 and logic 1 to pin 11. Clock pulse 1, output 0, 0, 0, 1. Clock pulse 2, output 0, 0, 1, 0. Clock pulse 3, output 0, 0, 1, 1. Clock pulse 4, output 0, 1, 0, 0. Clock pulse 5, output 0, 1, 0, 1. Clock pulse 6, output 0, 1, 1, 0. Clock pulse 7, output 0, 1, 1, 1. Clock pulse 8, output 1, 0, 0, 0. Clock pulse 9, output 1, 0, 0, 1. Thus, we connected the up counter. From the recorded readings, it is observed that the counter is counting up. Setting the decade counter to countdown mode and test. Feed the inputs of D0, D1, D2 and D3 with 1001 as binary values using toggle switches. This is equivalent to decimal number 9 as a set input for the down counter. Apply logic 1 to pin 5 such that the counter is now set for countdown operation. Refer to the tabulation and feed clock pulses at clock input pin 14. On feeding each clock pulse, record the output Q0, Q1, Q2 and Q3. LEDs on means logic 1 and off means logic 0. Set logic 1 to pin 5 and logic 1 to pin 11. Clock pulse 1, output 1, 0, 0, 0. Clock pulse 2, output 0, 1, 1, 1. Clock pulse 3, output 0, 1, 1, 0. Clock pulse 4, output 0, 1, 0, 1. Clock pulse 5, output 0, 1, 0, 0. Clock pulse 6, output 0, 0, 1, 1. Clock pulse 7, output 0, 0, 1, 0. Clock pulse 8, output 0, 0, 0, 1. Clock pulse 9, output 0, 0, 0, 0. Thus, we constructed down counter. From the recorded readings, it is observed that the counter is counting down.
Thus, we have constructed up-down synchronous decade counter and tested the operation by observing the output LEDs with reference to the truth tables. Thank you. Hi everyone, in today's video you will learn how to display the digit count values on 7-segment display using decoder or driver ICs. This video is split into two parts. Part 1 is single digit count values on 7-segment display and part 2 is 2-digit count values on 7-segment display.
At the end of this video, you will be able to construct and test a decade counter using IC74LS90 with a BCD binary coded decimal to 7-segment decoder, driver and 7-segment display. Construct a 2-digit counter and display the count value. Let us collect all the tools, equipment and materials required to do this practical. Digital trainer kit with user manual, IC74LS90 with datasheet, IC74LS47 with datasheet, 7-segment LED display with datasheet, male-to-male jumper wires, magnifying lens. Let us discuss about IC74LS90 and IC74LS47. IC7490 is a 14-pin dual inline package that can count binary numbers from 0000 to 1001. IC74LS90 is a 4-bit binary counter with a decade counter configuration. It counts in decimal, which means it goes through the numbers 0 to 9 in binary 0000 to 1001. Pin details of IC74LS90. Pin 1 clock input B, Pin 2 reset input 1, Pin 3 reset input 2, Pin 4 no connection, Pin 5 power supply plus 5 volt VCC, Pin 6 reset input 3, Pin 7 reset input 4, Pin 8 output QC, Pin 9 output QB, Pin 10 ground, Pin 11 output QD, Pin 12 output QA, Pin 13 no connection, Pin 14 clock input A. IC74LS47 is a 16-pin dual inline package. It is a BCD to 7-segment decoder driver IC commonly used in digital display applications. It is designed to convert a 4-bit binary coded decimal BCD input into the necessary control signals to drive a 7-segment display. Pin details of IC74LS47. Pin 1 BCD input B, Pin 2 BCD input C, Pin 3 active low display test input, Pin 4 active low blank output, Pin 5 active low ripple blanking input, Pin 6 BCD input D, Pin 7 BCD input A, Pin 8 ground, Pin 9 7-segment output E, Pin 10 7-segment output D, Pin 11 7-segment output C, Pin 12 7-segment output B, Pin 13 7-segment output A, Pin 14 7-segment output G, Pin 15 7-segment output F, Pin 16 power supply plus 5 volt VCC. Let us discuss about the 7-segment LED display. A 7-segment display is a type of electronic display device that can represent decimal numbers using 7 individually illuminated segments. Each segment is a small light-emitting diode or a similar technology. The arrangement of these segments allows for the representation of numerical digits from 0 to 9 and sometimes additional characters such as letters A to F for the hexadecimal displays. The decimal point segment is an additional segment on the display that is often used to represent decimal fractions or other symbols depending on the application. Let us discuss how to connect the IC74LS90 and IC74LS47 with 7-segment LED display. Check both the IC's part number using magnifying lens. Ensure that the pins of the devices are not bent or damaged. Identify pin 1 of both the ICs. It may have a small notch or dot to indicate pin 1 and align them correctly in the right position over the breadboard in the digital trainer kit. Gently insert both the ICs side by side along with the 7-segment display such that the dot pin is placed at right hand bottom corner. Start with the IC74LS90. Connect the pin 5 of IC74LS90 to plus 5 volt power supply VCC and pin 10 to the ground in the digital trainer kit. Next, connect the pin number 16 of IC74LS47 to plus 5 volt power supply VCC and pin number 8 to the ground. Connect the plus 5 volt to common terminal of 7-segment LED. Connect the pin number 11 of IC74LS90 to pin 6 of IC74LS47. Connect the pin number 12 of IC74LS90 to pin number 7 of IC74LS47. Connect the pin number 9 of IC74LS90 to pin number 1 of IC74LS47. Connect the pin number 8 of IC74LS90 to pin number 2 of IC74LS47 as per the circuit diagram. Connect pin 14 of IC74LS90 to the clock input. Connect pins 1 and 12 in IC74LS90. Connect pins 2 and 3 in IC74LS90 and connect it to input toggle switch S1 as shown in the circuit diagram. Connect pins 6 and 7 in IC74LS90 and connect it to ground point. Connect pin 13 of IC74LS47 to pin 7 of 7-segment LED for a A terminal through 100 ohm resistor. Connect pin 12 of IC74LS47 to pin 6 of 7-segment LED for B terminal through resistor. Connect pin 11 of IC74LS47 to pin 4 of 7-segment LED for C terminal through resistor. Connect pin 10 of IC74LS47 to pin 2 of 7-segment LED for D terminal through resistor. Connect pin 9 of IC74LS47 to pin 1 of 7-segment LED for E terminal through resistor. Connect pin 14 of IC74LS47 to pin 10 of 7-segment LED for G terminal through resistor. Connect pin 15 of IC74LS47 to pin 9 of 7-segment LED for F terminal through resistor. Connect pins 3, 4, 5 in IC74LS47 to plus 5 volt power supply. Switch on the plus 5 volt DC power supply. Apply logic 1 to the pin number 2 and 3 momentarily to reset the counter and observe the LED display. Apply clock pulse. Note down the segments of display and record your observations from 0 to 9. Clock pulse reset 7-segment display 0, clock pulse 1 7-segment display 1, clock pulse 2 7-segment display 2, clock pulse 3 7-segment display 3, clock pulse 4 7-segment display 4, clock pulse 5 7-segment display 5, clock pulse 6 7-segment display 6, clock pulse 7 7-segment display 7, clock pulse 8 7-segment display 8, clock pulse 9 7-segment display 9, and so on.
Thus, we have constructed and tested the single-digit count values using make connections between IC7490 and IC7447 with a 7-segment LED display as per the given circuit diagram.
Thank you.
In the last video, you learned how to construct and test the single-digit count value using decoder or driver ICs. Now, we are going to learn about the construction and testing of a decade counter using IC7490 and the construction and testing of a decoder or driver with a 2-digit count value on 7-segment display devices.
Construction and testing of a decade counter using IC74LS90. Identify the output LEDs as QA, QB, QC, QD in the digital trainer kit. Connect pin 11 of IC74LS90 to output LED QA. Connect pin 8 of IC74LS90 to output LED QB. Connect pin 9 of IC74LS90 to output LED QC. Connect pin 12 of IC74LS90 to output LED QD. Switch on the plus 5 volt power supply VCC. Reset the counter output by applying logic 1 input momentarily to reset input pins 2 and 3. Apply a clock pulse at pin number 14 using single shot logic pulsar and note down the output logic levels in tabulation at QA, QB, QC and QD. Also, note the corresponding decimal number displayed in the 7-segment LED display. Clock pulse input 0 reset, output 0 0 0 0, LED display output 0. Clock pulse input 1, output 0 0 0 1, LED display output 1. Clock pulse input 2, output 0 0 1 0, LED display output 2. Clock pulse input 3, output 0 0 1 1, LED display output 3. Clock pulse input 4, output 0 1 0 0, LED display output 4, clock pulse input 5, output 0, 1, 0, 1, LED display output 5, clock pulse input 6, output 0, 1, 1, 0, LED display output 6, clock pulse input 7, output 0, 1, 1, 1, LED display output 7, clock pulse input 8, output 1, 0, 0, 0, LED display output 8, clock pulse input 9, output 1, 0, 0, 1, LED display output 9, clock pulse input 10, output 0, 0, 0, 0, LED display output 0. Construction and testing of decoder driver with 7-segment display for 2-digit count value. This circuit requires 2 sets of IC74LS90 and IC74LS47 and 7-segment display devices. Start with the IC74LS90, connect the pin number 5 to plus 5 volt power supply VCC and pin number 10 to the ground in the digital trainer kit. Next, connect the pin number 16 of IC74LS47 to plus 5 volt power supply VCC and pin number 8 to the ground. Connect the plus 5 volt to common anode terminal of 7-segment LED. Connect the pin number 11 of IC74LS90 to pin number 6 of IC74LS47. Connect the pin number 12 of IC74LS90 to pin number 7 of IC74LS47. Connect the pin number 9 of IC74LS90 to pin number 1 of IC74LS47. Connect the pin number 8 of IC74LS90 to pin number 2 of IC74LS47 as per the circuit diagram. Make a short at pins 2 and 3 and also short at pins 6 and 7 to ground. Now connect IC74LS47 pins to 7-segment LED display 2 terminal through 100 ohm resistor. Pin 13 to A terminal. Pin 12 to B terminal. Pin 11 to C terminal. Pin 10 to D terminal. Pin 9 to E terminal. Pin 14 to G terminal. Pin 15 to F terminal. After the connection is over, label the 7-segment displays 1 and 2 as shown. Actually, pin number 11 of IC1 74LS90 is connected parallel to pin number 14 of IC2 74LS90 as a clock input. This triggers the display 2 for up counting once in 10 clock pulses subsequently. Display 1 will display 0 to 9 for every clock input and display 2 changes once after 10 clock inputs. Switch on the power supply plus 5 volt VCC. Reset the counter output by applying logic 1 input momentarily to reset input pins 2 and 3 and record the 7-segment output of 74LS47 and the number displayed on 7-segment display in tabulation. Apply a clock pulse at pin number 14 using single shot logic pulsar and note down the number displayed on 7-segment display in tabulation. Clock pulse input 0, reset, output 0000, LED display 1, output 0, LED display 2, output 0. Clock pulse input 1, output 0001, LED display 1, output 1, LED display 2, output 0. Clock pulse input 2, output 0010, LED display 1, output 2, LED display 2, output 0. Clock pulse input 3, output 0011, LED display 1, output 3, LED display 2, output 0. Clock pulse input 4, output 0100, LED display 1, output 4, LED display 2, output 0. Clock pulse input 5, output 0101, LED display 1, output 5, LED display 2, output 0. Clock pulse input 6, output 0110, LED display 1, output 6, LED display 2, output 0. Clock pulse input 7, output 0111, LED display 1, output 7, LED display 2, output 0. Clock pulse input 8, output 1 0 0 0, LED display 1, output 8, LED display 2, output 0. Clock pulse input 9, output 1 0 0 1, LED display 1, output 9, LED display 2, output 0. Observe that on giving the 10th clock pulse, display 1 changed from 9 to 0 and display 2 changes from 0 to 1. That is, the two displays show the decimal number 10. Thus, the two-digit counts go upward from 00 to 99 before resetting back to 00 again. By adding more 7-segment LEDs to the circuit, along with 74LS90, the display can display any numbers.
Thus, we have constructed and tested the two-digit count values on 7-segment displays along with counter and driver or decoder circuits.
Thank you.
Hi everyone, in today's video you will learn how to construct and test bidirectional shift register.
At the end of this video, you will be able to construct and test bidirectional shift register using IC74LS194. Let us collect all the tools, equipment and materials required to do this practical. Digital trainer kit with user manual. IC74LS194 bidirectional shift register with data sheet, male-to-male jumper wire, magnifying lens. Let us discuss the bidirectional shift register. A bidirectional shift register can shift data either in left or in right directions. In a left shift operation, data is moved from right to left. That means each bit shifted one position to left. The bit that was in the leftmost position is discarded and a new bit is shifted into the rightmost position. In the example, the most significant bit MSB is 1 and the least significant bit LSB is 0. Initial 1 0 1 0. After left shift 0 1 0 0. In a right shift operation, data is moved from left to right. Each bit shifted one position to the right. The bit that was in the rightmost position is discarded and a new bit is shifted into the leftmost position. In the example, the MSB is 1 and the LSB is 0. Initial 1 0 1 0. After right shift 0 1 0 1. Let us discuss about IC74LS194. This IC is available in 16-pin dual inline package with a 4-bit bidirectional shift register with parallel load capability. This bidirectional shift register is designed to incorporate virtually all of the features a system designer may want in a shift register. They feature parallel inputs, parallel outputs, right shift and left shift serial inputs, operating mode control inputs and a direct overriding clear line. Let us discuss the pin details of IC74LS194. Pin 1. Active low, master reset or clear input. Pin 2. Shift right serial input. Pin 3. Parallel input A. Pin 4. Parallel input B. Pin 5. Parallel input C. Pin 6. Parallel input D. Pin 7 shift left serial input. Pin 8 ground. Pin 9 mode select input S0. Pin 10 mode select input S1. Pin 11 clock input. Pin 12 output QD. Pin 13 output QC. Pin 14 output QB. Pin 15 output QA. Pin 16 power supply plus 5 volt VCC. Let us discuss how to make connections with IC74LS194 for left shift operation. Check the IC with the part number IC74LS194 using a magnifying lens. Identify pin number 1 of the IC. It may have a small notch or dot to indicate pin number 1. Align the IC correctly in the right position over the breadboard in the digital trainer kit. Gently insert both lines of the pins of the IC into the breadboard making sure each pin goes into a separate hole. Ensure that the IC is sitting flat on the breadboard without any pins bent or misaligned. Connect the pin number 8 to ground negative and pin 16 to power supply plus 5 volt in the digital trainer kit. Connect the pin 50 to output lead Q0, pin 14 to output lead Q1, pin 13 to output lead Q2, pin 12 to output lead Q3 in the trainer kit. Connect pin 3 to input toggle switch D0, pin 4 to input toggle switch D1, pin 5 to input toggle switch D2 and pin 6 to input toggle switch as D3 respectively. Connect the pin 11 to the clock input. Connect pin 2 to input toggle switch SR. Connect pin 7 to input toggle switch SL. Connect pin 9 to input toggle switch S0. Connect pin 10 to input toggle switch S1 as per circuit diagram. Connect the pin 1 to toggle switch as master reset input. When power is initially applied to a system, the master reset input can be activated to ensure that all the components start in the non state before normal operation begins. Switch on the plus 5 volt DC power supply. Apply logic 1 to pin number 7 for left shift operation. Using input toggle switches, load the data into the first flip-flop of the shift register as given in the truth table. Apply clock pulses to the shift register. Each clock pulse causes the data to shift one position to the left. Next, right shift operation. Now apply logic 0 to pin number 7 and logic 1 to pin number 2 for right shift operation. Using input toggle switches, load the data into the first flip-flop of the shift register as given in the truth table. Clock pulse given, observe the output LED set Q0 to Q3 is 1 1 1 1. Clock pulse 1 given, observe output as 0 1 1 1. Clock pulse 2 given, observe output as 0 0 1 1. Clock pulse 3 given, observe output as 0 0 0 1. Clock pulse 4 given, observe output as 0 0 0 0. Each clock pulse causes the data to shift one position to the right.
Thus, we have discussed the pin details of IC74LS194, constructed the bidirectional shift register, tested and verified the result with the truth table.
Thank you.
In the previous video session, we discussed about the pin details of IC74LS194 and constructed the bidirectional shift register as per the given circuit diagram. In continuation of this, in today's session, we are going to test a bidirectional shift register using IC74LS194.
Construction and testing of bidirectional shift register left shifting operation using IC74LS194. Switch on the plus 5 volt power supply. Set the input toggle switches as shown in the truth table for the left shifting position. D01, D11, D21, D31, SR0, SL1, S00, S11, MR1. Now set the mode select input S0 to logic 1 and apply the clock pulse to get the outputs Q01, Q11, Q21, Q31 as per the given data inputs D01, D11, D21, D31. Set the mode select input S0 back to logic 0, apply the clock pulse and verify the data is shifting to the left position as shown in the truth table. Clock pulse 1, output Q01, Q11, Q21, Q30. Clock pulse 2, output 1, 1, 0, 0. Clock pulse 3, output 1, 0, 0, 0. Clock pulse 4, output 0, 0, 0, 0. Let us discuss another example of a left shifting operation with different data inputs 1001. Set the input toggle switches as shown in the truth table. D01, D10, D20, D31, SR0, SL1, S00, S11, MR1. Now set the mode select input S0 to logic 1 and apply the clock pulse to get the outputs Q01, Q10, Q20, Q31 as per the given data inputs D01, D10, D20, D31. Set the mode select input S0 back to logic 0, apply the clock pulse and verify the data is shifting to the left position as shown in the truth table. Clock pulse 1, output Q00, Q10, Q21, Q30. Clock pulse 2, output 0, 1, 0, 0. Clock pulse 3, output 1, 0, 0, 0. Clock pulse 4, output 0, 0, 0, 0. Construction and testing of bidirectional shift register right shifting operation using IC74LS194. Switch on the plus 5 volt power supply. Set the input toggle switches as shown in the truth table for the right shifting position. D01, D11, D21, D31, SR1, SL0, S01, S10, MR1. Now set the mode select input S1 to logic 1 and apply the clock pulse to get the outputs Q01, Q11, Q21, Q31 as per the given data inputs D01, D11, D21, D31. Set the mode select input S1 back to logic 0, apply the clock pulse and verify the data is shifting of right position as shown in the truth table. Clock pulse 1, output Q00, Q11, Q21, Q31. Clock pulse 2, output 0, 0, 1, 1. Clock pulse 3, output 0, 0, 0, 1. Clock pulse 4, output 0, 0, 0, 0. Let us discuss another example of right shifting operation with different data inputs 1, 0, 0, 1. Set the input toggle switches as shown in the truth table. D01, D10, D20, D31, SR1, SL0, S01, S10, MR1. Now set the mode select input S1 to logic 1 and apply the clock pulse to get the outputs Q01, Q10, Q20, Q31 as per the given data inputs D01, D10, D20, D31, Set the mode select input S1 back to logic 0. Apply the clock pulse and verify the data is shift of right position as shown in the truth table. Clock pulse 1 output Q00, Q11, Q20, Q30. Clock pulse 2 output 0, 0, 1, 0. Clock pulse 3 output 0, 0, 0, 1. Clock pulse 4 output 0, 0, 0, 0.
In this video, so far, we have constructed and tested the bidirectional shift register using IC74LS194 and verified both the right shifting and left shifting operations of data with truth table.
Thank you.
Hi everyone, in today's video you will learn how to prepare digital circuit construction and electronic circuit construction using simulation software.
At the end of this video, you will be able to construct XOR gate using IC74LS04D, IC74LS08D, IC74LS32D by the circuit design and simulation software. Construct a bridge rectifier circuit using the simulation software. Let us collect all the tools, equipment and materials required to do this practical. Personal computer installed with simulation software. Printer with power and data cables. Construction of XOR gate using circuit simulation software. Select the circuit diagram of XOR gate for the construction using electronic circuits. Switch on the computer. Open the simulation software through the Windows Start menu or click on the simulator icon on your desktop and get the first screen. Observe the contents of the window and identify different menu items arranged horizontally on the toolbar as well as on the left side of the window. From the menu bar, identify the Place menu. Click and pull down the options as shown. Click on Component Group, select TTL and scroll to 74LS and select the required IC 74LS04D and click OK. Observe the dialog box table appearing inside the workspace area. Click on A and then OK. If more than one gate is required, click on A and B, etc. Follow the same steps and select the other required logic gates IC74LS08D and IC74LS32D from the menu as shown. To select the resistor, go to Place, select Component, set Basic in Group and select the resistor with the required value. Click OK. To add the power supply to the circuit, click on the Place menu, select Component, set Sources in Group, select DC Power and then click OK. To select an LED, click on Place menu, select Component, set Basic in Group, select 3D Virtual, select LED 3 green from the component and click OK. To select ground, go to the Place menu, select Components, set Sources in Group, select Power Sources and then select ground and place it in work area as shown. Select a logic switch by selecting Place, Component, Basic in Group, 3D Virtual and switch one from the component as shown. Make the wiring of the circuit. Keep the cursor at one node of the component. A dot will appear. Move the cursor to the place of wiring. The dot will appear at that node. Now click the mouse to finish the wiring. Follow the above step and complete the wiring of all the components. set the voltages to 5. You can set the required voltage of the power supply by double clicking on the symbol and then changing the value. Click OK. Label the input switch as A and B and output LED as output. Now simulate the circuit by clicking on the Run button from the toolbar, setting the different logic inputs at logic switches and verifying its output from the LED. Let us discuss how to construct a bridge rectifier using the circuit design and simulation software. Switch on the computer. Open the simulation software through the Windows Start menu or click on the simulator icon on your desktop and get the first screen. Look for the component toolbar or menu. It's usually on the left side of the screen. You can also use the place menu, component toolbar or place within box. Drag the components from the toolbar or menu into the work area. In the component library, locate the section for the diode. Identify the FWB, that is the full wave bridge. Select the bridge rectifier circuit and then place it on the work area. From the transformer menu, select a step-down transformer and drag it onto the design area by right-clicking on it. Set the ratio to 10:1, which means the voltage from the primary is stepped down 10 times. Select the appropriate resistor type from the toolbar menu. And by double-clicking on those components, and you can set their values as well. You can change the direction of the component by right-clicking on it and selecting Rotate 90 degrees clockwise or anti-clockwise as required as shown. Connect the transformer primary side to the AC supply as shown in the circuit diagram. And double-click on the AC source to configure its properties. Set the frequency and voltage values according to your simulation requirements. Connect the transformer primary side to the bridge rectifier as shown in the circuit diagram. Connect the transformer secondary side to the bridge rectifier as shown in the circuit diagram. Connect the resistor in parallel to the bridge circuit. To add the CRO to your circuit, select the instruments from the Stimulate menu and select the oscilloscope as shown. Click on it and then click on the location in your circuit where you want to place the CRO. Select a CRO that consists of two channels A and channel B. Connect channel A across secondary winding and channel B across the resistor. Run the simulation and observe the DC output across the load resistor. This will simulate your bridge rectifier circuit. The simulation will display the signals on the CRO screen. Once the simulation is completed, you can observe the rectified output across the load resistor. The waveform should show a rectified signal, which means the AC signal has been converted to DC. Connect capacitor across resistor and then run to simulation. The waveform will be a horizontal line. You will get the DC filtered by the capacitor, and this horizontal line is a filtered DC output.
In this video, we have constructed and tested the digital circuit X or gate using electronic circuit simulation, and also constructed and tested a bridge rectifier using simulation software.
Thank you.
In the last video session, we discussed how to construct an XOR gate and bridge rectifier circuit using the circuit design simulation software. In continuation of that, in this video, we are going to discuss how to construct a positive shunt clipper circuit using discrete components using the simulation software.
Construction of positive shunt clipper circuit using simulation software. Select the positive shunt clipper circuit by referring to the circuit as shown. Switch on the computer, double-click on the simulator icon on the desktop. Click on Semiconductor submenu and then click on Diode. Drag the diode into the user area. Double-click on the diode in the user area and click on the type. Select the suitable diode as shown and click on the OK tab. Ensure that the selected diode type number is displayed near the diode symbol. Right-click on the diode. Select Rotate Right if you want to place the diode in the vertical position. Click on Basic menu to select a resistor and click on Resistor. Drag the resistor into the workspace area. Double-click on selected resistor, type the value of resistor and click OK. Ensure that the selected resistor value is displayed near the resistor symbol. Keep the cursor at one of the resistor terminal and drag the mouse towards the terminals of the diode to make the wiring. If any component or device is edited by double-clicking on it, the symbol will appear in red color, otherwise it will appear in green color. Press Escape on the keyboard if you have clicked on any symbol which you don't want to use in the circuit. Click on the Sources menu to connect a voltage generator and voltmeters. Click on the voltage generator dialog box and double-click on the generator symbol. Click on Signal and then Unit Step dialog box. Click on the required waveform appearing in the pop-up window as shown. Click on Amplitude, Frequency and Phase to select the required value respectively and click OK. Click on Basic menu and then select Ground and place it in work area as shown. Click on Meter submenu and then click on Oscilloscope. Drag the oscilloscope into the user area. Make the wiring connections. Once your circuit and simulation parameters are set up, run the simulation by clicking on the appropriate button in the simulation toolbar. After the simulation completes, the oscilloscope window should display the waveform corresponding to the signals you connected it to in your circuit. You can analyze the waveforms to understand the behavior of your circuit. Next, let us construct a simple series clipper circuit using simulation software. Switch on the computer, open the circuit simulation software. Follow the step-by-step procedure and select a signal source, a resistor, a diode and a ground. Use the Place menu to select the diode tool and place a diode. Use the Place menu to select the resistor tool and place a resistor. Connect the AC input voltage source. Select the ground from the component menu and place it on the work area. Connect the components as shown in the diagram. Click on Simulate main menu, select Instrument submenu, then click on Oscilloscope and connect then as shown. Double-click on the signal source to configure its properties. Set the voltage and frequency according to your simulation requirements. After placing and connecting all the components, run the simulation by clicking on the Run button. This will simulate your clipper circuit. Click on the oscilloscope to view the output waveform of the circuit and analyze it.
Thus, we have constructed a shunt clipper and series clipper circuits
using simulation software.
Thank you.
Hi everyone! In today's video, let us learn how to list the defect and symptom in the faulty SMPS. Objectives. At the end of this video, you will be able to: Number 1. List the physical defects identified in the faulty SMPS in cold condition without switching it on. Number 2. Identify sections of the voltage stabilizer. Number 3. Locate the major components of various sections.
Let us collect the tools and equipment required to do this practical. Trainees toolkit, 1 set. Multimeter with probes, 1 number. Adjustable type table lamp, 1 number. Magnifying lens, 1 number. A faulty SMPS kit, 1 number. Oscilloscope, 20 MHz, 1 number. Soldering iron kit, 1 number. Spare components, as required. Rosin code solder, as required. First, let us carry out the safety precautions before doing this practical. Number 1. Disconnect the SMPS unit from the mains before removing from the PC. Number 2. Do not touch the PCB with bare hand without discharging the DC storage electrolytic capacitor. Number 3. Discharge the storage capacitor by using an incandescent bulb connected with wires across the capacitor. Take an incandescent bulb and connect it across the terminals of the storage capacitor. Ensure that the bulb's filament makes contact with both terminals of the capacitor. When the bulb is connected, it will briefly light up with full brightness as it draws current from the charged capacitor. As the capacitor discharges, the brightness of the bulb will gradually decrease until it goes out completely. Number 4. Do not use screwdrivers to short the capacitor terminals for discharging static charge. Number 5. Measure the voltage and make sure it is 0 before proceeding for test. Number 6. Set the multimeter in DC voltage mode and connect the red and black probes of the multimeter to the positive and negative terminals of the capacitor respectively. With the multimeter connected to the capacitor, observe the voltage reading displayed on the multimeter. If the capacitor is fully discharged, the voltage reading should be close to 0 volts. However, if there is any residual charge present in the capacitor, the multimeter will display a non-zero voltage reading. Procedure. Task 1. List the defect in the faulty SMPS in cold condition. Step 1. Record the specifications on the cover of SMPS. Step 2. Verify whether mains supply voltage is disconnected from the SMPS. Step 3. Initially, perform cold check by keeping SMPS in off condition. Components on PCB of the defective. Cold checking. In the context of switched mode power supplies, SMPS typically refers to the testing or troubleshooting of an SMPS when it is in cold state, meaning that it has not been powered on recently. Use an appropriate screwdriver to carefully remove the screws to take off the SMPS cover. Task 2. Observe the SMPS and list out the physical defects noticed as shown. Number 1. Charred or smoke smell on PCB. One common cause of the charred or smoke smell on a PCB is overheating components. This could be due to excessive current flow, poor heat dissipation, or a malfunctioning component. Number 2. Check for any component like resistor, diode, black or charged or damage in the PCB board. Number 3. Check for any capacitor in the PCB that is bulged or not. Exposing a capacitor to voltages or currents beyond its rated specifications can cause stress on the capacitor, leading to overheating and bulging. This can occur due to voltage spikes, power surges, or improper circuit design. Number 4. Check for PCB board darkened due to short circuit. Short circuits occur when electrical current bypasses the intended path and flows through an unintended route, often due to a direct connection between 2 points with different potentials. Task 3. Number 1. Check if the wires connected to the PCB boards were broken. Start by visually inspecting the wires connected to the PCB boards. Look for any signs of physical damage, such as fraying, cuts, or breaks in the insulation. Pay close attention to areas where the wires are soldered or crimped to connectors or terminals. Number 2. Check for any track cuts in the PCB. Look for any signs of physical damage to the tracks, such as breaks, scratches, or discontinuities. Use a magnifying glass to examine the PCB tracks, especially if the tracks are small or densely packed. Number 3. Check for any connectors broken in the PCB board. A broken connector may feel loose or wobbly, indicating that it is not surely attached to the PCB. Number 4. Check for any dry soldering points on the PCB board. Look for joints that appear dull, grainy, or have a rough surface texture. These are common characteristics of dry soldering points. Dry solder joints may feel brittle or have poor mechanical strength compared to properly soldered joints. Number 5. Check for any switching transistors blown into the PCB. Common causes of transistors blowing out include overvoltage, overcurrent, short circuits, or improper handling during installation or operation. Number 5. Check if the fuse is blown in the SMPS. If the fuse has blown in a switched mode power supply SMPS, it's an indication that there is a fault in the circuitry. Task 4. Number 1. Perform warm check of SMPS and measure output voltages. Number 2. Observe whether the SMPS fan is working or not. Start by visually inspecting the fan. Ensure that it is clean and free from any obstruction that may prevent it from spinning. Check for any visible signs of damage or wear on the fan blades. Number 3. Turn on the power to the SMPS. If the SMPS is installed in a computer or electronic device, power on the device. The fan should start spinning when power is applied to the SMPS. Number 4. Observe the voltages at the connectors and various test points and record the observation in tabulation. Number 5. Use a multimeter to measure the input and output voltage of the SMPS. Set the multimeter to the appropriate AC voltage range for the expected output voltage of the SMPS. Number 6. Start measurement of AC voltage across the 3-terminal mains cord. Serial number 1. Parameter to measure phase to neutral. Voltage AC 230 volt. Remarks. Number 2. Phase to earth 230 volt. Number 3. Neutral to earth 5 volt. Number 7. Set the multimeter to measure the DC voltage in the appropriate range and switch on the SMPS supply. Measure the DC voltage across the P4 cable connector and record the readings. Serial number 1. Description. Ground. Wire color black. Measured voltage. Number 2. Ground. Black. Number 3. Plus 12 VDC. Yellow. Number 4. Plus 12 VDC. Yellow.
Recap. In this video, we have learned how to list the physical defects identified in the faulty SMPS. Thank you for watching.
Today, I will be discussing how to go for concrete mix design. It is an important aspect of civil engineering to ensure proper strength and durability of the concrete.